In order to prove these two, we have to find the transfer functions of both of these.
Of both of them, right.
And then do what with that, with the transfer functions?
What you're going to end up with is you're going to have...
on the back.
You're going to have function A, which is... Both of them are going to be the same, by the way. Function A of omega times function B of omega. And then that is going to be minus or plus some constant. So what you're going to end up with is minus some constant times, and I'm sure you guys probably have seen this before, the way that you can write this, you can either make it a unit step function like this. And what this simply means is that this thing will go high after, if this minus this is positive, this right here can go to whatever the amplitude is.
Okay.
But you follow what I'm saying, right?
Yes.
In other words, because you're looking at these two numbers. But typically this is in the time domain, but you can also do it in the frequency domain.
Okay.
Okay, and so that's what this is looking at. Look like basically you have two limits. One limit is defined by this op amp, the other one is defined by this op amp.
Okay.
So this is the top limit, this is the bottom limit.
Okay.
Can you explain again what you were saying about those going to high?
This right here going high. Okay, what's happening is, because of the way this diode is polarized, the only way that it's going to conduct is that this node has to be more positive than that node, right? The only way this node is going to be more positive, this node is approximately at 0 because this resistor, if you look at it, there is no voltage source here, so this node is at approximately 0 volts. The only way this diode is going to conduct is that this node right here has to go to 0.6 volts or higher. The only way that's going to happen is that the voltage here has to be less than the voltage here. So remember, the op amp has a gain that's approximately infinite, right? And so the only way you can get a positive voltage here is that this voltage is less than that voltage. Because the way, if you look at an op amp, you have plus and then you have minus. And let's say this is VA, and let's call this VB. And so you have a diode out here like this, like in that example. The only way you're going to have a voltage right here is that you have VA is greater than VB. And when that happens, this node will go positive. And when that node goes positive, this diode will conduct. Because, see, what's happening is the circuit is actually taking VA minus VB and then multiplying it by the gain of the circuit. Okay? And so that gain is approximately infinite. So let's just say, for the sake of argument, that is 10,000. So you have 10,000, 10 to the 4th power times VA minus VB. And you need that to equal to 0.6 volts to turn that diode on, right? Well, if you take this and divide it into this thing, what you're going to find is that these numbers can be very close, but you still need this number to be larger than that number for this to happen. Okay? And so what this thing is doing is actually checking the limits of the voltage that's applied to these input nodes. Okay? One limit, like I said, is defined right here. When this node right here is more negative than this voltage, then this one will come on. When this voltage right here is more positive than this node, then this diode will come on. But they don't both come on at the same time.